Hi everyone. This is the review chapter for section 2, and we did a good number of this already in our class meeting. So I'm just going to kind of scroll through. You can pause and reread the notes. But this is what we had discussed in our virtual meeting that we had, our Zoom meeting. So we left off here, so I didn't cover this. So this is what's new. So we're going to start with the domain of a variable. The domain of a variable is the set of all values that a variable may assume is called the domain. So these basically are the values that you can place into an expression and it'll be true, or it will be a valid answer. So the big thing you always want to think about with domain is that you never want the denominator equal to 0. So you never want your denominator can never equal 0. The other thing about domain is if you have a square root, you always want whatever's inside that here. So whatever's inside has to be greater than or equal to 0. So those are the two components. So notice that in this question it says the domain of the variable in the expression here, you can't have 3. So the domain is the set of all real numbers such that x cannot equal to 3. So that's how you read it. X such that x cannot be equal to 3. Because if x was 3, the denominator wouldn't be 0, which is undefined. So when you have these types of questions, you basically have to just take that denominator set equal to 0. Whatever you find, that's what you place there. So let's say we have this question. In the formula for the circumference, C of a circle is equal to the diameter, and it has to have the formula here, which is supposed to be pi, but it didn't show up on the graphic. So the domain of the variable d represents the diameter of a circle, is a set of all positive real numbers where the diameter has to be greater than 0. So you may say, well, where did that come from? Well, let's just think about this. If you got a circle, this diameter can't be less than 0, and it can't even be equal to 0, or else this circle wouldn't exist. So oftentimes in the word problems that we're going to be working with throughout the term, the domain really also has to do with, well, what possible values can I use? Because does it make sense if it's something else? So that's where this comes from. So let's now, the same idea with circumference, right? Because circumference is a measurement of the outer part of the circle. Well, that also has to be greater than 0. Can't be equal to 0, can't be less than 0, or else it wouldn't exist. So we're going to talk about the definition of a, and it's supposed to be, again, I apologize, when I imported it, it didn't work. So a to the n and a to the 0. So these are exponents, so a to the n, a raised to the n power, a raised to the n power, and similarly, this is a to the 0 power, and this should be a to the 0 equals 1. Right, so basically we're talking about exponents, right? So if a is raised to some number and n is a positive integer, you're going to be multiplying it by itself n times, right? So if this was 2, you would have 8 and a. If this was 5, you'd have a, and that's how you multiply it. One of the big rules that we'll also revisit again throughout the course is that whenever you raise a number to the 0 power, it's always 1. A lot of this should be somewhat a review that you should remember from your past math life. This is a to the negative n. This should be a negative n exponent. So remember, if you have a negative exponent, you can change its place in the fraction. So technically, this is over 1 right now. If you change its place in the fraction, so if you switch it, this exponent now becomes positive. Now, I always like to show, what if it was the other way around? So what if it was negative n here? Well, if I switch its placement on the fraction, the exponent changes, regardless of where you go. Once you move its place from one level to the other, the sign of the exponent has to change. So let's look at this question, and again, the notation came a little weird, so I'm going to just show you that this should be 3 to the negative 2, and see how then it drops down to the denominator with a positive exponent, and 3 squared is 3 times 3, which is 9. Similarly, this is x to the negative 3, and you drop it down, so it becomes x to the positive 3. Now this, notice that it changes its place in the fraction, because you can really think of it as that. And then this becomes 1 squared all over 4 squared, which is 1 all over 16. And then remember, when you divide a fraction by a fraction, it's the same thing as multiplying by the reciprocal. So if you have 1 all over m all over n, it's the same thing as 1 times the reciprocal. And that's what you have here, because this becomes 1 times 16 over 1. And that's how you get just 16. So let's look at this theorem. The whole portion up here on the top we have to just fix. So let me adjust this. So this first theorem should be a to the m times a to the n is equal to a to the m plus n. So that's the first one. The second one, which is here, should be a to the m raised to the n power is a to the m times n as one exponent. That's your second. Your third one would be, let's say you have ab raised to the n power. Well, that n, because it's multiplication within the factors, it's a to the n times b to the n. Number 4 is right here, and it's already written properly. So when you have a to the m divided by a to the n, so it's sort of like number 1, only operation is division. Well, then you subtract exponents. Here, when it's multiplication, you add exponents, but here, division, you subtract. You could also switch its placement in the denominator. The reason why that happened is that you would change it to a negative exponent. And when you do distribute the minus sign, you get a to the negative m plus n. And then just switch their places and you get exactly that, okay? And the same thing with this number 5 here. This is very similar to the 3 here. Only difference is that you have division. And so the n will get placed with each term. You're only allowed to place it when it's multiplication or division, not if it's addition. Okay, so if addition or subtraction, you're not allowed to do that. So let's take a look at this question. I'm going to just rewrite these again because they did not come right here. So this is x to the negative 4th times x to the 6th. Well, when you multiply like bases, you add their exponents. So you get x to the 2nd. Let's take a look at this one. I'm going to rewrite it so you can make sense of it. So it's x to the negative 4th raised to the 2nd power. So when you raise a power to a power, you multiply. So you get x to the negative 8th. And then you say, oh, well, I can drop this baby down and change its exponent, and it becomes positive. Let's take a look at this one now. This would be 3x raised to the 3rd power. So you put that exponent since it's multiplication with each term. 3 to the 3rd is 27, and x to the 3rd stays. Same thing, since it's division, you can place it with each of them. So it's 3 to the 5th all over 4 to the 5th. And that actually is written out here for you. Okay, let's look at the next one. So when you divide like bases, you subtract exponents. So it's going to be negative 3 minus negative 7. So that's negative 3 plus 7. And that's how you get 4. So you'll have some questions that say write each expression so that all exponents are positive. So the first thing I usually like to say is look for your like terms. So you have x's and you have y's. So you're going to have 4 minus 2 and then negative 3 minus 1. So that's basically what we see here. 4 minus 2, negative 3 minus 1. So then you do the 4 minus the 2 and you're left with x to the 2nd. And then you do negative 3 minus 1, you get negative 4. But realize you want positive exponents. So this one right here you have to change and you bring it down and then you write them together. Okay. Similarly, this question is very similar. So you have division. You have the whole fraction raised to the negative 3 power. So you're going to put the negative 3 to each factor. Okay, so that's what you see here. You have first placing with the denominators, and then you're going to place the negative 3 with the 2 and with the x to the negative 2nd. Usually people forget this guy. Don't leave him out, right? He has to also have the exponent placed with it. The negative 3 times negative 3 gives you the 9. The negative 2 times negative 3 gives you the 6. 2 to the negative third is 1 all over 2 to the third, which is 1 over 8. And then when you divide a fraction by a fraction, you're going to multiply by the reciprocal, so that's how you get the 8 in the top. The y to the 9th stays, the x to the 6th stays, and that's your final answer. So oftentimes in this course, we're going to be working with the principal square root, which means if you have b squared is equal to a, the principal square root of a is b, which means you just want the positive one, right? So you want to keep the answer to be positive. Is the square root of 16 positive at negative 4? Yes, but the principal square root would just be 4. So as you see here in this example, yes, technically you have plus or minus 6 would be the answer, plus or minus 2/5, plus or minus 5.7. However, the principal square root is just these. So the square root of a squared is equal to the absolute value of a, where a is any real number when we're dealing with the principal square root. And so you see that here. So 3 examples. If you're using a calculator, be comfortable with trying to do that notation. You usually have to use that little upper caret in your calculator to bring your exponent, and it'll italicize this, and then you place that number in. Scientific notation is written as a number times 10 to some exponent. If the exponent is positive, then it's a large number. If the exponent is negative, then it's going to be a super tiny number. Not a negative number, but tiny, like in quantity, right? Quantity. To change a positive number into scientific notation, you count the number n of places that the decimal point must be moved to arrive at the number x, where you want your x to be big, one or greater, but no greater than no, you can't reach 10. So usually we just say 9 point something. If the original number is greater than or equal to 1, the scientific notation is going to be x times 10 to the nth power. And then if it's between 0 and 1, the notation is 10 to the negative nth power. So let's write each number in scientific notation. So the first thing is you put a decimal right there. So we're going to 8.471. So see how the number is large? Now it's tinier. So you're going to want to raise it by 10 to some positive number, and you just count the number of times you scooped, and that was 3. And then you see that here in this answer. Here, since the number is between 1 and 10, or it's greater than 1, you have a positive exponent. Let's try this on. Oh, I think I skipped. Okay, letter B. The decimal point in 2.134 is between the 2 and the 1. Since the number is already between the 1 and the 10, the scientific notation is just 10 to the 0 power, right? Because you don't want to change it. So it's still the same number times 10 to the 0. Remember, 10 to the 0 is 1, and you get the same answer back. Okay, let's look at this one. You're going to want to change it to 3.76. So the number went from smaller to bigger. So you're going to want to, it wants to be smaller. We scooped it just one place, so it's negative 1. And I do articulate here that since the number is between 0 and 1, you have the negative exponent. Let's try this one. So I put the decimal right here. So 6.52. I scoop it 1, 2, 3, 4, and it's going to be negative 4. So write each number as a decimal. Let me just fix the exponents. So this will be a positive 3, right? So the number is going to be bigger. So it's 3, 1, 2, 3. So 3, 6, 0, 0. Same thing here. We scoop it other direction. 1, 2, 3, 4. 1. So So we have all those scoops here. Hold on one second, a little bit of technical difficulties. Okay, so then we scoop it, 1, 2, 3, 4, and then we have 0.000621, and that's your answer. And again, this is going to be, here's your decimal, so scoop a 3, 1, 2, 3, so 0.001, and as you see that there. Okay, so let's try this example. The height of Mount Everest is 8,848 meters. The height of Mount Everest is about, put the decimal here, so you scooped it 1, 2, 3 times, so that's why it's going to be 10 to the third power. The diameter of an atom is about 1 times 10 to the negative 10th power. Express this as a decimal. So you take that 1 and you scoop it 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice 1, 2, 3, 4, 5, 6, 7, 8, 9 with the 1. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1 meters. And that's the end of section 4R2.